another example where we're going to be computing probabilities. This time we're going to be looking at a contingency table. The contingency table here below summarizes the data from 200 randomly selected seniors from a high school. It displays two variables, their plans after graduation and whether or not they place. When we arrive to our final answer, we're going to be rounding to 4 decimal places. Now, are you surprised to see a contingency table with two variables? We're not surprised to see that because we use contingency tables when we're keeping track of more than one variable. The first variable, which is sports, has two categories, one being play sports, the other one being does not play sports. The other variable, which is plans after graduation, has 3 categories, college, directly to work, and gap year. One thing to mention is that if a senior says that they play sports, if they're in this category here, then they're not going to be in the category does not play sports. So it's either one or the other. One senior cannot be in both categories. We're going to assume that that is the case for the other variable. We're going to assume that a senior, it's either going to go to college, directly to work, or take a gap year. We're not going to have a senior under 2 categories. Seniors, each senior has to select one category. So that's going to be important for some of the probabilities that we're going to compute. We're going to be asking ourselves for the probability of selecting a senior out of the 200 such that, and then we're going to have some characteristics about that senior. Here, the random process is selecting a senior from the 200. Let's say that Julissa is one of the 200 students. And let's say the Samantha is one of the 200 students. And we can have, Jose, Matthew, Justin, right? We have 200 seniors. Each senior is going to be one of the outcomes. We're randomly selecting a senior. The probability of selecting Julissa out of the 200 or Justin out of the 200 or Samantha out of the 200, the probability of selecting any of the seniors is the same. I really want to emphasize the idea because we can only do theoretical probabilities if we are assuming that all outcomes in the sample space are equally likely outcomes. And we do have equally likely outcomes. With that being said, we're ready to compute some probabilities. What is the probability of selecting a senior who's taking a gap year? Let's go ahead and write this using probability notation. P of, here I'm just going to write gap. P of gap here represents the probability of selecting a senior who's taking a gap year. This is going to be equal to the number of ways you can select a senior that is taking a gap year. That is the number of seniors who are taking a gap year. Again, just to keep it short, I'm just going to write number of seniors who are taking gap. We are going to be dividing by the number of outcomes in the sample space. The number of outcomes in the sample space is the total number of seniors. So what is the number of seniors who are taking a gap year? Let's go ahead and look at the contingency table. Here we see that under gap year, we have a total of 20 seniors. We see that 5 of them play sports, 15 of them don't play sports. For this problem, we're not interested on whether they play sports or not. We just want to know how many seniors are taking a gap year. So here we're going to have 20 out of the total number of seniors, which is 200. This is equal to 0.1. You could also write this as a percentage. We would have to multiply 0.1 by 100, and that would give us 10%. The probability of selecting a senior who is taking a gap year is 10%. One thing that I want to emphasize here is that we are taking the number of outcomes in the event space divided by the number of outcomes in the sample space. Let's go ahead and look at part B. What is the probability of selecting a senior who's taking a gap year and going to college? Let's write this using probability notation. Let's write probability of gap and college. This probability is equal to the number of seniors who are taking a gap year and going to college. Again, here I'm just trying to keep it short, so I'm just going to write number of seniors who gap and college. And we're dividing by the total number of seniors. Now here's my question. What is the number of seniors who are taking a gap year and going to college? Okay. Now some of you might be looking at the value 140 and the value 20. And you're saying, well, I have 140 students going to college and I have 20 students taking a gap year. But here, you're selecting one senior. Do you have one senior who's doing both, who's going to college and taking a gap year? That is the question here. The answer to this question is no, we don't have anyone under both categories, right? We don't have a senior under both categories, under the gap year category and the college category. So here, how many seniors do we have who are taking a gap year and going to college? The answer here is 0. And here we're dividing by 200. This is equal to 0, which is equivalent to 0%. Let's make a note to ourselves here. We have 0 seniors who are both taking a gap year and going to college. That is why our probability is 0. The probability of me selecting a senior who's under both of those categories is 0 because we have 0 out of the 200 who land in both of those categories. Now let's look at part C. What is the probability of selecting a senior who's going directly to work or going to college? Here we're saying we want to select a senior who's either going to work or a senior who's going to college. Here, we're not saying we want a senior who's in both categories. Okay? So that is the difference between and or. And here above represented that we wanted a senior to be in both categories. Here below, the word or represents that we're okay with selecting a senior in either one of the categories. Let's go ahead and write this using probability notation. We're going to write P of work or college. Here we're going to write the number of seniors who, I'm just going to write work, number of seniors who are going to work, plus number of seniors who are going to college. This represents the number of outcomes in the event space. This is going to represent the total number of seniors, those are our outcomes, that are either going directly to work or going to college. And then we're going to be dividing by the total number of seniors. So let's look at our table. How many seniors are going to work? Here on the table, we see that a total of 40 students are going directly to work. So we have 40 plus how many seniors are going to college? Here on the table, we see that a total of 140 students are going to college. So on the numerator, we have 40 plus 140. On the denominator, we have the total number of seniors, which is 200. This is equal to 180 divided by 200. This is equal to 0.9, which is equivalent to 90%. The probability of selecting a senior who's going directly to work or a senior who's going to college is 90%. Now let's go ahead and take a look at another problem. In part D, we're being asked, out of all the seniors who are going to college, what is the probability of selecting a senior who plays sports? This first part of the sentence is really important. We are being told, don't look at all 200 students. Only look at the students who are going to college. So I'm already telling you that I know the student that we selected goes to college. Our sample space is no longer going to be all 200 students. We're not selecting a student from all 200 students. We are selecting one senior from the 140 students who are going to college. We are restricting the sample space. We're going from 200 to only looking at 140 students. Out of those 140 students, out of the students who are going to college, what is the probability of selecting a senior who plays sports? Let's go ahead and write this using probability notation. You might be wondering, how are you going to write that? Let me write, what is the probability of selecting a senior who plays sports? And then I'm going to write this symbol here. This is a vertical line, which represents that given something already happened. The given part here is that we know that the senior is going to college. So here I'm going to write college. Now, in a future lesson, we're going to talk about conditional probabilities. We're going to have a rule for conditional probabilities. Conditional probabilities are probabilities where something is given. This is a conditional probability. I'm adding this question here because I want to show you that even though you haven't seen the conditional probability rule, the formula for that rule, if you have a contingency table, you can answer this question without having the conditional probability rule. As I mentioned before, here we're selecting a student who said they're going to college. So on the denominator, our sample space is the number of students who are going to college. On the numerator, we want the number of students who play sports and college. Here on the numerator, I have the number of students who play sports and are going to college, right? And let me emphasize the idea here. Why is the sports and college here? Why? Because we're talking about the probability of selecting a student who plays sports given that they're going to college. So we are only focusing on this column here. We only want the students who play sports and are going to college. We're going to take that value and we're going to divide by the number of students who are going to college. Here, if I just write the number of students who play sports on the numerator, you're going to think that I'm referring to all students who play sports, which is the 50 students who play sports and go to college, the 30 students who play sports and are going directly to work, and the 5 students who play sports and are taking a gap year. That would be a total of 85. Here I'm being really specific. We're not looking at all students who play sports. We're looking at students who play sports and go to college. Here below, we have 50 students who play sports and are going to college divided by the number of students who are going to college, which is 140. This is equal to 0.3571. We can also write this as a percent, which is 35.7143. Notice here, when I wrote it as a decimal, I made sure to have 4 values after the decimal point. When I wrote it as a percent, I made sure to have 4 values after the decimal point. That is why I didn't just write 35.71%. So this one was a little bit more difficult. One thing that I want to emphasize is that for this question, they were telling us to restrict the sample space. Don't look at all 200. Only look at the seniors who are going to college, because we're being told out of the seniors who are going to college. Okay, so out of this group, what is the probability of selecting a senior who plays sports? So whenever you work with conditional probability, you're going to be restricting the sample space. Again, we're going to see this idea later on in another lesson. Now, what is the probability of selecting a senior who's going to college? I'm going to let you do this one on your own. I might add a few more questions below this video just to have you practice doing theoretical probabilities. Again, I will make sure to write a solution below the question. In order for you to see that solution, you need to submit the assignment. Once you submit the assignment, you can go back and review your answers and the correct answers, and you can see the solutions below the questions. Now, let me mention some of the properties of probability. The first one being that the probability of an event, the probability of A, has to be between 0 and 1. It can be equal to 0 and it can be equal to 1. Okay? So it can be 0, it can be 1, or anything between 0 and 1. If P of A is equal to 0, that means that the probability of A is 0%. Now, if P of A is equal to 1, then that means that the probability of A is 100%. Okay? So here we're saying the probability cannot be less than 0%, the probability cannot be more than 100%. If the probability of A is equal to 1, that means that the probability of event happening is 100%. That means that it always happens. If P of A is equal to 0, that means that event A never happens. The probability of event happening is 0. Now, what would happen if I take the probability of each outcome and I add those probabilities? Okay? In other words, what happens if I sum the probability of each of the outcomes? We're going to get 1.